So we started with OSPF in our last session, a bit about OSPF. Just let's get into the that recap quickly. Okay. So we started with the full form of OSPF. We know that OSPF stands for Open Shortest Path First, right? And open means it's an open standard, and shortest path first is an algorithm which is called as the Dijkstra algorithm. And using the shortest path first algorithm, any routers who are running OSPF can find the shortest path towards the destination, right? Which is basically how OSPF works. It's a layer 3 protocol, okay, and it's a layer 3 protocol which has an IP number of 89, right? It is a classless protocol. Classless protocol meaning that it supports default classes, that is class A, class B, class C's default address mask, that is 255 or sorry slash 8 slash 16 and slash 24 address mask, as well as any other address mask other than this, which is basically what you call it as classless, right? Its AD value is 110, okay, administrative distance value, right? And in an interview sometimes they ask what is the meaning of administrative distance. Okay, why is administrative distance important? So, for example, let's say I have couple of not couple of routers, two routers, R1 and R2. Okay, and between R1 and R2, I'm running different protocols. Let's say I'm running EIGRP, I am running OSPF, okay, and I'm running BGP. Okay, let's say I'm running eBGP between them. Okay, between R1 and R2. So all these routers, so not all the routers, all these protocols are exchanging the same data. Okay, they are exchanging the same data with each other. So which protocol will these routers choose to send the data, right? From a router's perspective, they can choose only one particular protocol to forward the data. And if they have multiple protocols running inside them, they should choose one protocol. Okay, now in such a scenario, they would go for the AD value, which is called as the administrative distance value. Whichever protocol has the lower AD value, that particular protocol is sorry, that particular protocol is chosen to forward the data. Now EIGRP's AD value is 90, OSPF's is 100, and eBGP's is 20, right? Now obviously the lowest of them is eBGP, and R1 and R2 will choose eBGP protocol to forward the data. All right, let's say eBGP fails. For some reason eBGP fails, the next better or the next lower AD value is of EIGRP, so R1 and R2 will choose EIGRP to forward the data. If EIGRP fails, then they would switch over to OSPF, which has an AD value of 110. So AD value, or the administrative distance value, is used as a tiebreaker if multiple protocols are running between two different routers and they're forwarding the same kind of data. Okay, its OSPF's multicast address is 224.0.0.5. It also uses a multicast address of 224.0.0.6, right? And it is also called as a link state protocol. Okay, we'll discuss about link state in detail later, but just to let you know what a link state means. A link state protocol means that it will forward or it will share the information of its links. Meaning, for an OSPF, this interface is a link because it is connected to R2. If R1 has many interfaces that has connectivities, for R1 or for OSPF running on R1, all these interfaces are links. So R1 will share the state. R1 will share the state of these links with R2. Similarly, R2 will share his own state of the links with R1, right? And that is how they will know each other's state, or they will know each other's links and their states. That is why this is called as a link state protocol. Now imagine if I have R3 over here, R3 also has different links. So what R3 is going to do, R3 will share the information of these links or the information of states of these links with R2. R2, along with its own links, will also share the information of R3's link to R1. Similarly, whatever information R1 is sending to R2, R2 is forwarding that to R3. So what is happening? R1 automatically knows about R2, and it also knows about R3. Similarly, R3 automatically knows about R2, and it also knows about R1. Right. So R1 knows what are the links that are R3 connected to. R3 also knows what are the links R1 is connected to. Right. So when all the routers which are not directly connected, if you see here, R1 and R3 are not directly connected. When two routers are not directly connected and they are sharing information about each other through a particular protocol, that kind of protocol is known as a link state protocol, because all the routers are sharing their information about links to each other. Thereby, all the routers in the network know about how other routers are connected. That is what a link state protocol means. Okay. Then the OSPF uses concept of areas. Again, we'll talk about area at a later stage in the session. It also supports ECMP. ECMP means equal cost multipathing, meaning that from R1, let's say from R1 to R50, okay, there are many ways to reach R50. Okay, there are many ways to reach R50, right? So let's say, okay, do not assume that they're just four routers, because I have written 50, meaning that between R1 and R50, there are other routers as well. And it has lot of ways to reach R50. Similarly, R50 also has a lot of ways to reach back to R1. So as we know that OSPF runs on the shortest path, right? Let's assume R1 has multiple shortest path to reach R50. So R1 can choose all the paths, all the shortest path to reach R50. That is what you call equal cost multipath. All right. So this is what we had looked into yesterday. And now going into a bit of a general discussion. Okay. Sometimes in interview they ask, which is a better protocol, OSPF or EIGRP, right? Or OSPF or BGP. But I'm not going to discuss with BGP. The reason is that BGP is an EGP protocol, not EBGP. It's EGP protocol, external gateway protocol. OSPF, ISIS, EIGRP, RIP, they all are IGP protocols, internal gateway protocols. So I'm comparing two internal gateway protocols, or the most prominent internal gateway protocols, that is EIGRP and OSPF. So what is the difference between EIGRP and OSPF, and why is OSPF majorly preferred? Let's try to understand that. So over here, think this is a network, okay? And in this network, we are running EIGRP. Okay. Now, if R5, okay, first of all, please understand, as I said, all the IGP protocols, their main concern is for sending the data in the shortest way possible, right? And trying to get the information of each and every destination. These are the major characteristics of every routing protocol. So let's say if a data from R5 needs to be sent to R3 over here, right? So it has multiple ways to send the data to R3. And with EIGRP calculates the shortest path. We know that EIGRP calculates the shortest path through different parameters, right? It uses bandwidth, it uses jitter, delay, okay, delay, load, and reliability. These are the 5 factors that EIGRP uses to find the best path to reach from R5 to R3. All right. Now, not just R5 and R3 are going to use this thing. Every router in this network are going to use these 5 parameters to find the best path to forward the data. Now, what is happening here is that when a particular data comes, let's say a data comes, it says the destination IP is R3, right? So R5 here will find out the destination IP and will use all these parameters to find the next best router. Okay, so R5 is going to find if R12 is the best router to reach R3, or is it R14, or is it R6. Now let's say it assumed R14 is the best router. So it will forward the data to R14. R14 will again calculate using these 5 parameters, which is the best next hop, right? So let's say it is R11, from R11 to R16, R16 to R13, right? So what is happening? Every router is calculating these, using these 5 parameters, every router is calculating the next best hop. So what is happening? All the routers are consuming some kind of processing, right? Their CPU processing is increasing because they're using 5 different parameters to calculate the best path, right? That is one of the problems with EIGRP. Why EIGRP is not majorly used? First problem. Second problem is that EIGRP is majorly used in the enterprise section. You can see here, I'm not sure if you can see it. Okay. EIGRP is majorly used in the enterprise section. Okay. OSPF is majorly used in the service provider side. I'm not saying that OSPF is not at all used in enterprise. It is also used. However, when when obviously when the competition is between OSPF and EIGRP, right? EIGRP is preferred in the enterprise side, whereas OSPF is preferred in the service provider side. And why is that? Because when we are talking enterprise, we are talking the enterprise section from a LAN perspective. Okay. Or the if you remember, we were talking about the 3-tier architecture in our early session, right? Tier architecture, 3-tier architecture, where we had the access layer, distribution layer, core layer, right? So that was our enterprise section. In there, we prefer using EIGRP. Why? The reason is that because when the data is entering into your network, or when the data is leaving out of your network, you want the data to travel through the best path. Okay, when it is traveling from the best path, you do not want any delay. You want the best bandwidth. You want the least jitter. You want the least load, and you want the best reliability for the data to transfer from your core router to the end user, that is you sitting on a computer. So in order for the data to be sent using the best bandwidth, best reliability with least load, delay, and jitter, the only protocol that calculates using this is EIGRP. That is why most of the time EIGRP is preferred on the enterprise side, because we want the data to travel as fast as possible inside your lab. Okay. Now, what is the problem with EIGRP in the service provider side? Why can't I use EIGRP in the service provider side? First, the problem itself is with its metric calculation, or these 5 different parameters that it uses. In a service provider network, let's say instead of this is a service, imagine this as a service provider network. Now, from R5 to R3, I want the data to travel as fast as possible. Okay, I'm not thinking it should have a less delay, it should have more reliability, it should have better bandwidth. No, I'm not thinking all these things. In a service provider network, you know that there are 1,000, 10,000 lakhs of routers in the network, and you're sending data from one geographical location to another geographical location, probably from one continent to other continent. Okay, so you want your data to be sent as fast as possible. when you want the data to be sent as fast as possible, your router needs faster processing. With EIGRP, what happens? Every data that it receives, it is going to calculate these 5 different parameters. So what happens when it uses all these 5 parameters to calculate? It is using the processing. When it uses processing, your forwarding time becomes slow. Your forwarding time becomes slow. Your data is received, your router is now calculating all these things and then forwarding. So it takes up some time. No matter how fast your router is, how powerful your router is, it is still taking a fraction of seconds, which is again a big, a big factor in a service provider network. I want my data to use the shortest path, and it should be as fast as possible. That is the requirement in service provider side, and that is why we do not use EIGRP. Another thing, in a service provider network, as I said, there are a lot of devices in the network. And what happens in EIGRP, if it goes beyond 700, 800 routers in the network, right, the processing of EIGRP becomes very slow. So imagine what is going to happen in the service provider network. Let's say R5 fails for some reason. Okay, for some reason, the link between R5 and R6 fails. Okay, so what R5 is going to do? R5 is going, if you know about EIGRP, right? EIGRP is going to send a query. Query is basically, it is asking other routers, does it know an alternate path to reach R6? Because the link between R5 and R6 had a failure. So R5 is going to ask, do you know an alternate path to reach R6? Similarly, R6 is also going to send this same query to all the adjacent routers. All these adjacent routers are going to forward the query to all their adjacent routers. Okay, now imagine the load that is going to come on R1. It is going to receive all the query messages from all the routers. Imagine that load on R1, right, which is not necessary. Okay, then R1 is going to reply saying that I know, but it is a long shot, because R1 has a lot of different ways to reach R5 and R6. It can say any other path. It can choose any path. It can reply to all the queries saying, yes, I know how to reach R5 and R6 via this path. This path meaning the path which is best for R1. Okay. For R1, it has a best path to reach R5 and R6. It is going to respond to all the query message using that best path only. However, again, it's a waste of time for R1. Why? Because R5 and R6 directly connected router R14 is going to say, yes, through me, you have the alternate path to reach each other. So what was the point of that query message being sent to R1 all the way? There was no point. So what is happening? The messages in EIGRP are consuming a lot of data of the router, not required. Correct. So these are few of the problems which is why EIGRP is not used in the service provider network. And the major reason is EIGRP is Cisco proprietary. Okay, it is a Cisco proprietary protocol. And in a service provider network, we know that not just Cisco devices are present. You have Cisco, Juniper, Aruba, HP, IBM, Nokia. There are a lot of devices there are a lot of vendor devices in the network. Obviously, all the vendor devices should be able to send data to each other without compromising, right? So they would require a protocol which is open to every other vendors, right? There should not be interoperability issue. That is why again EIGRP is not preferred in the service provider and is preferred in the enterprise section more. Right. Now, how is OSPF going to solve this problem? As I said, you can divide in OSPF, you can divide your whole network into smaller regions, and that region is called as area. Okay. Now with this area, what is the advantage? So as I mentioned, let's say if the link between R5 and R6 fails, R5 is going to ask other routers in that are adjacent to it, do you know how to reach R6? Okay. Now what happens is that this message that R5 is asking, do you know, is limited only to its own region, right? It is not going to be forwarded to other regions in the network. That is the advantage of OSPF. So your area is basically limiting the flow of your control messages towards different regions. So what happens? The overhead on R1 is not present at all. It doesn't care what is happening between R5 and R6. Right. So that is one of the reasons why we prefer OSPF in the service provider network. Second reason, as I said, it's an open standard, meaning any vendor can use it. And that is why it's the most popular choice to deploy in the service provider network. Because it is open standard, you can deploy any other protocol over it. You can have MPLS running over OSPF. You can have BGP running over OSPF. Right? You can have different protocols running over OSPF without the worry of interoperability. This is the reason why we use OSPF in service provider side. Any question here before we jump into the next section? Okay. So moving on, as I said, OSPF runs on the concept of areas. Okay. So we'll start with single area OSPF first. And as I said, let's not dive into the concept of area as of now. Okay. So we'll jump into single area OSPF, but I'll explain what is the actual meaning of area at a later point of time. So single area OSPF. Now OSPF, as we had discussed in yesterday's class, OSPF works based on the interface that you're connected with, right? So you have serial interfaces, then you have Ethernet interfaces, and then you have loopbacks, right? So OSPF considers serial interface as point to point, okay, and Ethernet interfaces as broadcast, and loopbacks as stub, meaning it's a terminal. A terminal meaning the network is ending there. So we had discussed this yesterday, and I'm not going to dive more into it. Okay, so let's move to the next part. Okay, now OSPF. So first let's start with the point-to-point OSPF, single area OSPF, right? And you can see in the diagram we have two routers, R1 and R2 over here, right? R1's loopback address is 1111, R2's loopback address is 2222. 12001 is R1's interface IP, 12002 is R2's interface IP. And we are using a serial interface, and that is why it's a point to point. All right. Now, let's directly jump into the configuration, and we'll discuss more and more from there. So we get inside the R1's or any router's CLI, we type the configuration terminal, press enter, and to enable OSPF, we write router OSPF 1. With this command, what happens? We know that OSPF is enabled, right? And this 1 means the process ID. 1 is a process ID, and we can write any process ID between 1 to 65535. I can write any process ID between 1 to 65535. But what is the significance of this process ID? What is the significance of this process ID? So let me visually show you what a process ID looks like. So for that, let me open my task manager. Okay, let me open my task manager. So you can see here that All right. So you can see here that these are the processes that are running on my system, right? And every process, okay, every process has a number. Okay, it has an ID to it. All these processes that are running on my computer will have their own IDs, right? That is the same thing with OSPF process ID. So when you enable OSPF, right, you are saying that I'm running an OSPF and you're manually mentioning that use the process ID 1. So in the router's RAM, there is a space dedicated for OSPF, which has a process of 1. This means that I can run different OSPF processes on the same router with different process IDs. Okay, starting from 1 up till 65535, I can run these many OSPF processes with different process ID. This also means that OSPF 1 process is different from OSPF 2, from different from OSPF 3, and different from OSPF 65535. Okay, so two different OSPF processes can exist on the router. And to differentiate these two processes, OSPF processes, we use the process ID. That is the significance of this process number. So OSPF process 1, and then we write the router ID. It is again optional. There is no need to choose or write the router ID as optional. Router ID is nothing but a kind of a name that the router chooses to introduce itself to other routers. Okay, how does it introduce itself? We'll talk about that in some time. All right. Now, if you do not write the router ID manually, router ID is chosen by the router automatically. So router ID election also takes place. Router ID is elected first based on the highest loopback address. On the router, if there are many loopback addresses, whichever loopback address is the highest, that loopback address is chosen as the router ID of the OSPF. If there is no loopback address present on the router, then the next is highest
Physical
active,
address.
active physical address. Okay, physical IP. This is chosen as the router ID of the router. Okay, so let's say I do not have a loopback address, I do not have a router ID configured. So for R1, when OSPF is enabled, it will choose 12001 as the router ID for itself. Okay. Now, once you do this, we type the network command. Okay, we type the network command like this: network 12.0.0.0.0.255.255.255 area 0. Leave the concept of area for now because we are talking about single area. Okay, leave the concept of area for now. Now, what is the significance of the network command? It is also very important to understand. 12.0.0. What is the meaning of this? So, just like our IP route that we saw yesterday, IP route 12.0.0.0.255.0.0.0 is the network that we want to send the data to, right? But here you can see that this thing is the opposite of your address mask, and it is called as a wildcard mask. It's the opposite of a address mask. Now, some interviewers, they'll ask you question, okay, why cannot we use the wildcard mask as such? What is the point 12? Why can't I just simply write 255.0.0.0? Why do I have to write 0.255.255.255 as the wildcard mask? To be very honest, even I do not know. But I know this is how it has been designed. This is how all the routing protocols have been designed. Okay, so to be very honest, I have no answer why wildcard masks are written in the opposite manner. I have no idea. There may be a solid reason. I have not looked for it. If you have time, please go ahead and search for it. Okay, to be very honest, if you find that answer and if you have that knowledge, it's a great knowledge. I have
I
not got I have not gotten time to find that out why wildcard masks are written in the opposite manner. Yeah, Prashant.
I think looks like suppose you have given right 12 network in /8 subnet. So
Hmm.
if like on my routers there are two or three more interfaces, right, which
Hmm.
are connected to different network devices,
Hmm.
and suppose on that interface I have given a network of 12.0.0. Slash 14, 16, right? Whatever network I have given
Hmm.
configured there.
Hmm. Hmm.
Then when we are configuring the network command with this area, right? Area with the network command. So
Hmm.
with the wildcard mask, when we are putting, right? Basically,
Hmm.
I think what I believe the first octet in the wildcard mask is 0. So basically, we are matching when we are putting this network, right? It will enable the OSPF on all the interfaces which are a part of which are a part of network 12.
I understood what you're saying. Okay,
Yeah.
which is basically what we are going to see in the next thing, the significance of network command. But my question is, why do
Mm-hmm.
we write it 0.255.255.255? Why can't I just write wildcard mask as 255.0.0.0? It still
Okay.
means the same thing.
Yeah.
Still means the same thing,
Mm-hmm. Yep.
right?
Mm-hmm.
So my question is, I don't have an answer why it is written in the opposite manner.
Mm-hmm.
Okay, why can't I just simply write it as in this straight manner, like a like an address mask?
Yeah. I got your point. Yeah.
Right. So I do not have an answer for it. If like I have not gotten time to search for it on the internet also.
Mm-hmm.
But if you find the answer and if you know it, it's great to have that
Mm-hmm.
answer.
Yep. Sure.
Now, as I said, what's the importance of this network command, and why is it important to understand the logic behind it? So Prashant, he just mentioned the crux of it, right? So let's try to understand what is happening with the network and the wildcard mask, and how is OSPF basically working with the network command. Now, these are the network commands that we are going to look at. Okay, and these network commands are running on R1. All right, these network commands are running on R1. So let's see what is basically happening. So here, the first network command says 10.1.0.0 and 0.0.255.25. All right. Now here, what the OSPF is thinking, that where in the wildcard mask, wherever there is zero, just write down those octaves. Okay, and ignore the rest of the octaves. Again, wherever there is zero in the wildcard mask, write down that octet and ignore the rest of the octaves. Okay, and find out all the interfaces. Find out all the interfaces which have an IP address starting with 10.1. Again, find out the interfaces which have IP addresses starting with 10.1. So on R1, we can see this is 10.1, 10.1, 10.1, 10.1, and 10.1. So what is going to happen is OSPF will be enabled on all these interfaces, and we'll discuss about a message in just a few moments. OSPF starts to send hello messages out of all the interfaces. Okay. So first thing the network command does is enable OSPF on the corresponding interfaces. Interface, right? Second thing that it does, send hello message out of those interfaces. These are the two things that the network command basically does. So if you do not understand, it's okay. We'll move to the next network command. It will be easier. So the next network command says 10.0.0.0.0.255.255.255. Okay. So OSPF again sees the address wildcard mask wherever there is 0. Copy that value and ignore the rest of the octets. Now what OSPF is going to do, it will look for all the interfaces which have an IP address starting with 10. Okay, so here again, all the interfaces on R1 are starting with 10, 10, 10, 10, 10. So again, out of all these interfaces, OSPF will be enabled and it will send the OSPF hello messages. Okay, it will send OSPF hello messages. All right, now the next is 0.0.0.0. Okay, this is a very confusing command. Okay, instead of 255, just think at as 0.0.0.0. Address mask is 0.0.0.0. Okay, now here what is happening? OSPF, as I said, wherever there is 0, it will copy down all the octets. But we know that 0000 is not an IP address at all. That means OSPF will send OSPF will be enabled on all the interfaces irrespective of the IP address. Irrespective of the IP address. Let's say you have two interfaces where here you have a 20 network and here you have a 30 network. But in the network command, it has been mentioned 0.0.0.0, which is not a valid IP address. But OSPF thinks it has to enable OSPF on all the interfaces irrespective of their IP address and the network. And it will also send OSPF hello messages out of all the interfaces. Yeah, Prashant, you're saying something?
No, sir. Sorry.
Yeah. The next is 10.1.13.0. Okay, and 0.0.0.0.255. Okay, I'm just writing 255 as 2 in short. Okay, so wherever there is 0, note down that value 10.1.13.0 and ignore the rest. So here what OSPF is going to do, whichever interface has an IP address starting with 10.1.13, only on that interface OSPF will be enabled. So here you only have this interface which has the IP address starting from 10.1.13.1. So OSPF will be enabled on this interface and hello message will be sent out of this interface only. Only. Okay. The next is 10.1.13.1 and the wildcard mask is 0. So 1. So here what OSPF is going to do, it is going to look for this exact IP address. And that interface is this. And out of this interface, OSPF hello messages will be sent. And on this interface, OSPF will be enabled. The rest of the interfaces, they will not be part of OSPF. And through those interfaces, OSPF messages will not be sent. And this is why the network, understanding the network command is very, very important. Network command is very, very important to understand. Now, in real time, you may not see only 255s in the 255, 255, 255 dot sorry, 0.255 or 0.0.255.255 or 0.0.0.255. You may not see this in the real time. Just like our address mask, we had a difficult address mask, right? Where you, instead of 255, you had 248 or 192 or 224, something like that. In real time also, you may see such interfaces or such IP addresses or address masks. What are you going to do? Okay, what are you going to do? So let's imagine you have, let's say there is an IP address. Let's say instead of 10.1.13.1, okay, you have 10.1.13.1. This is /24, which is 255.255.255.0. Okay. Now, just to give you a small tip, how is the wildcard mask created? How is the wildcard mask created? Just to give you a tip, subtract every octet by 255. So you have 255 minus 255 is 0, 0, 0.255. This is your wildcard mask. Very simple. So now, if you have any address mask, any other address mask other than just 255, you know how to calculate the wildcard mask for that. So let's say 255.254.0. This is the address mask for this IP address. Find out the wildcard mask. Easy. Subtract every octet by 255. So you have 0, 0. The last octet is 255. This is 5 minus 4 is 1. 5 minus 2 is 31. So this is your wildcard mask for this address. 0.0.31.255. Okay. And the router will automatically calculate what are the interfaces which are coming into this subnet mask, and it will enable OSPF only through those interfaces only. Okay, very simple. You do not have to worry about how OSPF is going to calculate. All you need to understand is finding out the wildcard mask and how the network command is helping OSPF send the hello messages and enabling them on the required interface. I hope with this explanation, the network command is clear.
Yes.
Now, I have been talking about after the network command, OSPF sends hello messages, OSPF sends hello messages, OSPF sends hello messages. Let's understand what exactly is hello message. So once you enable OSPF using this command on R1 and R2, for example. So what R1 is going to do, R1 will enable OSPF on this interface and it will start to send OSPF hello messages. OSPF hello messages. Now, what are the contents of a hello message? Okay, or what exactly is a hello message? Hello message is nothing but introducing yourself, saying that, hi, my name is this. Okay, I live in this address. Okay, and this is my address, and basically a router is introducing it, right, by sending a hello, right? So when you meet someone, right, you introduce yourself, you say hello, hi, then you introduce yourself, and then you say you work here or you live here, etc. All that introduction. So similarly, when using a network command, if the network command is successfully executed, the OSPF is enabled on that interface, and OSPF sends OSPF hello messages to that interface. Now, what are the contents? This may be an interview question, so just pay attention. Contents of a hello message. Okay. First, router ID. Okay, we know how router ID is elected. So router ID is chosen, right? Then the IP address, then the subnet mask. Okay, the subnet mask, the hello timers. Okay, the hello timers, the dead timer,
Area.
area, right? These are the few main parameters that are sent in a hello message. Okay, now why are these parameters important? Because when R2 also enables OSPF and sends a hello message, right, they both check, are my parameters same? Okay, the hello message that I have received from the other router, is his parameter similar to my parameter or not? Okay, if it is similar, then only I can be a neighbor with him, then only I can be an adjacent, I can form an adjacency with him. We'll talk about neighborship and adjacency in just a while. Then only I can be a neighbor with him, then only I can be an adjacent, can form an adjacency with him. So R2 also sends these important information in its hello message, right? So over here 1.1.1.1 is R1, R2 is 2.2.2.2. Okay, IP address is 12.0.0.1, here 12.0.0.2. Subnet mask is /24, here is sorry, not 24, /8, and this is also /8. Hello timers. Hello timers is the timer. The default timer is 10 seconds, meaning that at every 10 seconds interval, R1 is going to send OSPF hello messages at 10 seconds of interval. Okay, so here also it is 10 seconds. That timer is basically 4 times the hello timer. So this is 40 seconds. Here also it is 40 seconds. Now area. If two routers want to be neighbors, they have to be in the same area, just like you and your neighbor. Okay, me and my neighbor are in the same society, are in the same building, are on the same floor. That is why we are neighbors. Okay, I cannot call you guys who are sitting in a different city as my neighbor, because obviously we are not in the same city. Okay, let alone the area. We are not in the same city. How can we be neighbors? Right. So if two routers want to be a neighbor, they should be in the same area. So here, as I said, we'll talk about the area concept in just a while. Not probably today, probably tomorrow. Okay. So the area should be same, 0 and 0. So the router's ID, the router ID, it should not be same. The router ID should not be same. The IP address cannot be same, obviously. The IP address cannot be same. The subnet mask, they should be same. The hello timers, they should be same. The dead timers, they should be same. And the area, they should be same, in order for the two routers to understand each other's hello messages. If these parameters or these conditions, they do not agree, let's say if both the routers have the same router ID, the hello message will fail. If the subnet mask is not same, the hello message will fail. If the timers or if the area is different, the hello message will fail. Okay, so it's basically like I am introducing to my neighbor, this is my flat number, okay, and this is my address. Okay, and let's say I go out. Okay, I will keep on calling, I will meet you 3 times a day, or let's say here instead of 10, I will meet you 10 times a day. Okay, I will meet you 10 times a day, right? And we both are on the same floor. So even my neighbor would say, this is my address. Okay, and even I will also meet you at 10 times a day. And I am also living on the same floor. So we basically are neighbors. If any of these parameters, if I go and talk to someone who's on the 10th floor, obviously we both are not neighbors. So these parameters should match in order for the two routers to start exchanging and understanding each other's hello messages. Clear? Any question up till here?
No.
Okay. So now, after the two routers, R1 and R2, okay, once OSPF is enabled and they start to send OSPF hello messages, what are the things that happen? Now, the two OSPF routers, there are two types of, what do you say? Okay, I would say there are two types of neighborship that they form. Okay, I know neighborship is not the correct word. I cannot recollect the right word. Okay, I cannot come up with the right word.
Adjacency.
Not adjacency also.
Mm.
I'll just call it neighborship. Okay. So there are two types of neighborship. Obviously, the first is neighborship.
Mm.
Okay. Second is adjacency. Right.
Mm.
I cannot come with a two single word to define these two things. Okay. Anyway, to form these two neighborship or adjacency, let's try to first understand what is the meaning of this neighborship and adjacency. So you met a friend. Okay. Yeah. So let's say you met someone. Okay. Let's say a friend. Okay. You're meeting for the first time. So what you did, you introduced yourself, right? You said hello, hi, how are you, I'm living here, I'm living there, etc. You introduced a general introduction with each other, so you just became friends. Then as days passed by, you started sharing information with each other. You started sharing personal information, you started sharing professional information as well, and slowly you started becoming best friends, right? That is the difference between OSPF neighborship and OSPF adjacency. Okay, so two routers are neighbors at an initial stage, and later, after some time, they become best friends, forming adjacencies. So to become friends first, they have some criteria. Then to become best friends or to become the adjacent or create adjacency, they have some criteria. Those criteria are called as states. All right, and we will look into those states now. So R1 and R2 over there, right? When you enable OSPF, right, they will send hello message. Okay, so what happened? The moment I enable OSPF on R1, R1 sends the hello message. Okay, and when it sends the hello message, it goes into a state called as the init state, which is also called as the initialization state, meaning that it is initiating the hello. It is initiating the friendship. Okay, it is sending the hello message. Similarly, when you enable OSPF on R2, R2 is also going to send the hello message. Thereby, it is also moving into the init state. They both are in the init state now. Now, R1 sees hello message from R2. Okay, and we know what are the information that it is seeing in the hello message: the router ID, the address mask, the subnet mask, area, hello timer, dead timer, etc. And when all those parameters are matched or the conditions are satisfied, R1 moves into a state called as two-way state. It moves into a two-way state. Similarly, R2 will also see the hello message from R1. When it sees the parameters matching, it will also move into a two-way state. This basically is called the neighborship. Neighborship in OSPF. This is what you call it as neighborship in OSPF. So neighborship meaning they have just become friends. They exchanged the hello. They saw each other's router ID. They read each other's address mask, the IP address, the address mask, hello timers, dead timer, and the area. Okay, and they found the matching parameters and the non-matching parameters to be fine. So they move into a state called as two-way state. Okay, now once they move into a two-way state and once the criteria is all fulfilled, they move into a state called as ExStart state. ExStart state. All right. Now, in this ExStart state, there are few things that are negotiated. Okay. Now, till two-way, it was the neighborship that was formed between the two routers. Now, with the ExStart state, the adjacency will be slowly formed between the two routers. Adjacency will be slowly formed between the two routers. So, to finally have the adjacency, few things are to be matched or negotiated. So in the ExStart state, the first thing that they negotiate is who is going to be the master and who is going to be the slave. Now, what is the concept of master and slave? As I said, in a link state protocol, OSPF is a link state protocol, right? So R1 here, let's imagine R1 is connected to different links. R2 is also connected to different links. Now R1 will be sharing the information of these links to R2 and vice versa, meaning R2 is also going to share these link information with R1, right? Now, when the two routers are sharing this information, they decide who is going to be the master and who is going to be the slave, meaning that this sharing of information is not a two-way communication. It is not a two-way communication, it's a unidirectional communication. So for a unidirectional communication, there should be a source and there should be a destination. Source is the master, slave is the destination. Okay. Again, please understand the exchange of the data between R1 and R2. They share the information of the links that they're connected with. It's a unidirectional exchange. If it's a unidirectional exchange, that means one of the devices is going to be the source, the other is going to be the destination. So whichever device is the source, he is the master. Whichever device is the destination, it is going to be the slave. So these two routers need to identify for this unidirectional exchange of data and find out who is going to be the source, who is going to be the slave, meaning who is going to be the master and who is going to be the slave. Okay, so whichever router has a higher router ID, higher router ID becomes the master. Higher router ID device becomes the master. And in our case, R2 has a higher router ID and hence R2 will become the master. And slave is R1. That means R2 will send the information or share the information with R1. Okay, and R1 in response is going to send back that information. So again, it's a unidirectional. R2 sharing that information with R1. It's done. When that is done, R1 is going to share its information with R2. So again, it's a unidirectional. It basically tells who is going to initiate that sharing of information. And that initiation is always done by the master. And master is decided based on whoever has the highest router ID. All right. Then the Second parameter that is decided on is the DBD sequence number. DBD sequence number. DBD sequence number is basically decided based on whoever is the master. Whoever is the master will decide the sequence number. Okay. Now, what is DBD? DBD stands for database descriptor. Database descriptor. So database descriptor is nothing but a small description of the database. So R2's connected links is its database. R1's connected links is its database. So R1 and R2 are going to share the database information with each other. But before sharing the whole database, they share just a small description of the database. That is what you call it as database descriptor. All right. In order to even better understand it, I have a very good example. All right. So let's say that there are in usually there are in a class there are few people who like to gossip a lot, right? So let's go back to the time when we were in 7th class or 8th class, or probably let's say 9th, 10th class, where we used to gossip a lot. Okay, especially what is happening inside the class and what is happening outside the class. Okay, so let's say this is student A and this is student B, and they gossip a lot. They know what is happening inside the school and outside the school also. Okay, so let's say that A right, A suddenly has an information saying that the sports teacher in the school has a crush on the English teacher of your class. Okay, a very funny example. The sports teacher, right, has a crush on the English teacher of our class. Right? So this is a news, right? A comes to know about it. So what A does, A goes to B and he says, "Do you know? Do you know?" Right? Do you know that our sports teacher has a crush on our English teacher? Do you know? So basically, A is giving just a small hint of the whole database. The database has all the gossip. Okay, how it started. Okay, how it started, and how did A know about it? How did A know about it? Who all knows about it? There are a lot of things that is inside this. But the first information, do you know that the sports teacher is having an affair or not having an affair, has a crush on the English teacher? Okay, so that's a small description to B. Now, if B already knows about it, okay, if the student B already knows about this, he will say, "I know." So what happens? Student A is not going to share any of this information because B already knows about it. But what if B does not know? If B does not know that the sports teacher has a crush on English teacher, what is he going to say? "Tell me." Or I should say, "Tell me," with a big caps. Tell me. Now A is going to share all this information. How it started, how did A know, who all knows, does the English teacher know that the sports teacher has a crush, or is it a unidirectional, or is a one-way crush, or a two-way crush, or it's a unidirectional crush, or it's a bidirectional crush? All that information will be shared when B says, "Tell me." But before B asks for the whole information, A is just sending a small description. Do you know? That is exactly what the DBD here is. When R1 and R2, before they exchange the database of all the links that they are connected to, they will send a small description about these links. Do you know about this link or not? If not, I will share you the information. If yes, it's okay. That is what DBD means. So database descriptor is basically a small description of the links that a particular router is connected to. As simple as that. Any question? What is DBD? I hope the analogy is enough to understand.
Yeah. Yes.
Okay. So here what happens is that the DBD sequence number, the master and slave, they both, when OSPF is enabled, when the two routers, they move into an ExStart state, they will call themselves as master, saying that I am the master. I will initiate it. And this is my DBD sequence number. But when the two routers see each other's router ID, they will come to know that one of them has to be a master. And in our case, R2 has become the master. So R2's DBD sequence number will be chosen, meaning that both the routers, the slave and the master, both of them will call themselves as master first. Please remember this. They will call themselves as master first. Okay. So when they share this, when they are in the exchange state, they will send the hello message, or they will send this DBD, database descriptor, where they will call themselves as master, MS. This bit is called the MS bit. If we open the DBD bit in the OSPF, we will see this as MS, calling themselves as master. I am the master. And I will initiate the exchange of DBDs. Okay, I will initiate the exchange of DBDs. But when R1 comes to know that, it is not the master, it is the slave. So when the next DBD is exchanged, we'll talk how DBDs are exchanged in a while. When the next DBD is exchanged, in R1's DBD, this MS bit and this I bit will not be present. MS bit and I bit will not be present. MS bit means the router is calling itself as the master. And because it is calling itself as the master, it will also initiate the exchange of DBDs. It will initiate the exchange of DBDs that it decided. Clear? Then the last factor that is negotiated is MTU, maximum transmission unit. Obviously, the MTUs on both the routers should be same. Very simple. If any of these parameters, okay, mostly in an interview they would ask, if a router is stuck in an ExStart state, what does it mean? Very simple answer, meaning that the two routers have the same MTU. Sorry, the two routers have a different MTU. Now, a follow-up question. It is my requirement. The interviewer says it is a network requirement that the two routers should have different MTUs. Now, what can I do? I still want the OSPF to start. I still want the OSPF to start, but the MTUs should be different. What can I do? So in Cisco, I'm not sure about other vendors, but in Cisco, you have a command called as MTU ignore. It's an interface command, IP OSPF MTU ignore. It's an interface command. When you execute this, the routers will ignore the MTU size. It can be same, it can be different. However, MTU will not be a negotiating factor. It will be completely ignored. So these three parameters are negotiated: master and slave, the DBD sequence number, and the MTU. These are negotiated in the ExStart state. When this negotiation is completed, they move into the next state called as the exchange state. So now exchange state and ExStart state, basically you can say it is the starting of the exchange state. That is what is called as ExStart state. It is the starting of the exchange state or the starting of the exchange. In the exchange state, basically your DBDs are exchanged between the two routers. That is why it is called the start of the exchange of DBDs. It is starting. It is not start. I mean, it's just the start. The DBDs are not yet exchanged in the ExStart state. The DBDs are exchanged only in the exchange state. Okay. So here what happens? The DBDs are exchanged between the two routers. R1, what it does, let's say R1 has multiple links, right? R2 also has multiple links. So R2 is going to share DBDs about these links to R2. R2 is also going to share the DBDs of its link with R1. That is what you call it as exchange. However, there is a catch here. As I said, the master and slave election has happened in the ExStart state. And the exchange of these DBDs is unidirectional. Only one way the data can be sent. Either R2 will send the data or R1 will send the data or the DBDs here. And how is that happening? So as I said, in our case, R2 is the master and R1 is the slave. And R2 will initiate the exchange of DBDs, right? So let's say this is link number 1, link number 2, link number 3. For R1, this is link number 4, this is link number 5, this is link number 6. So what R2 is going to do, when R2 sends its own DBD, okay, R2 is the master, he will share his DBD number 1. Okay. Now, in response to DBD number 1, R1 is going to share his DBD number 4. That means until and unless the master shares his DBD, the slave cannot send its own DBD. Master will send the DBD. Slave will send its own DBD as a response. Now, the next, R2 is going to share DBD number 2 in response. R1 is going to share DBD number 5. Then R2 will share DBD number 3. R1 is going to share DBD number 6. This is how your DBDs are exchanged. Master router will share his DBD. The slave router will share his DBD as a response. Now, a trick question in the interview. Listen to this carefully. Let's say that R1 has three more links, 7, 8, and 9. But R2 only has 3 links. So here what happened? R2 has shared all his DBDs, DBD number 1, DBD number 2, and DBD number 3. R2 does not have any more links connected to it, so he is not going to share the information of those links, or it does not have any more DBDs to exchange with R1. But R1 has 7th link, 8th link, and 9th link to share it with R2. How is it going to do? It cannot send it by its own because it's a slave. Until and unless master sends a DBD, R1 cannot send back its own DBD. What is R1 going to do in this case? I hope the question is very clear. Let me repeat. The master has less links and the slave has more links. The master has completed sharing all its DBDs. However, slave still has more DBDs to exchange, but the slave cannot send the DBDs until and unless master sends a DBD, right? So here in this case, how is R1 going to share the DBD about 7th, 8th, and 9th link to R2? This is where your more bit comes into picture. So in your DBDs, you have three types of bits. In your DBD, you have three types of bits. We just discussed master slave bit, initiating bit, and the third bit is M bit, which is called as the more bit. This is initiate bit, and this is the master slave bit. The master slave bit is used during the master slave election. Similarly, the initiate bit is used during the master slave election, right? This we know. Now, this is the third bit, more bit. How is it used? So whenever the slave responds, it sets the M bit to 1, meaning that it has more DBDs to exchange. Let me repeat it again. Whenever the slave responds to the master, it sets the M bit to 1, saying that I have more DBDs to share with you. So when R1 sends the DBD number 4, it sets the M bit to 1. When it sends the DBD number 5, it sets the M bit to 1. When it sends the DBD number 6, it sends the M bit to 1. Now, when this DBD number 6 is received by R2, it knows that R1 has more bits to exchange with me. So R2 will send an empty DBD. It will not have any information. It will send an empty DBD. Now, R1 has a DBD from R2. So R1 can respond. Now, when R1 responds, it will send back DBD number 7 with the M bit as 1. Okay, with the M bit as 1. Now, R2 will again receive it. It will understand that R1 has more bits to exchange. Again, it will send an empty DBD. R1 will send back DBD number 8 with M bit as 1. Again, R2 will send an empty DBD. For that response, R1 will send DBD number 9. But here, this time, since all the DBDs that R1 had has been shared with R2, this time the M bit is going to be 0, meaning that it has no more DBDs to exchange. So with this, all the DBDs with R2 and R1 has been exchanged with each other. I hope this is clear. Now, after your DBDs have been exchanged, okay, the two routers go into a state called as loading state. Both the routers go into the loading state. Here, then what happens? With the DBDs that they have received, R1 has received R2's DBDs, R2 has received R1's DBDs. As I said, they are just small descriptions, right? So R2 knows R1's DBDs, right? What were the R1's DBDs? R1's DBDs were 4, 5, 6, 7, 8, and 9. And R1 had R2's DBDs. What were R2's DBDs? DBD number 1, 2, and 3. Now, if R1 does not know about these DBDs, it will R2 is the master, right? When R2 obviously does not know about 4, 5, 6, 7, 8, 9 DBDs, right? So it wants the whole database. So R2 will request, it will send an LSR, link state request, for DBD number 4. In response, R1 will send a link state acknowledgement. Okay, link state acknowledgement with the whole database of number 4. These are R1's database. These are R2's database. Okay, so R2 is requesting for R4 DBD, or the database of the whole, or the database of link number 4. So as a response, R1 will send back the whole database for R2. Now here, R1 can also request the master slave is only till exchange state. Now in the loading state, R1 can also send a link state request for DBD number 1, 2, and 3. In response, R2 will send a link state acknowledgement for the whole database of 1, 2, and 3. With like this, what will happen? R1 and R2 will both exchange the database of the link. Previously, in the exchange state, they exchanged only the DBD, the description, but here they're exchanging the whole database. Now, once the whole database is exchanged, right, they go into a state called as full state. Full state, meaning that now both of them have received each other's database. They know about each other's link. They know about each of the links database as well. This is what you call it as adjacency. Adjacency. So as I said, OSPF has two types of neighborship. One is the normal neighborship in the two-way state, and then you have adjacency in the full state. So in the interview, you may be asked, what are the states of OSPF? So you start explaining each of these states, and now you also know what are the factors that are involved in each and every state, and what are the things that are happening inside each and every state. Okay, so in the init state, the two routers move into the init state when they see each other, when they send the hello. They move into the two-way state after the hello parameters are matched, and they become neighborship, forming a two-way. Then they move into an ExStart state. In the ExStart state, there are few factors that are negotiated. Master slave is negotiated with the MS bit and the I bit, right? Whichever router has a higher router ID becomes the master, the lower router ID becomes the slave, and the master router chooses the sequence number. Then MTU should be same. If it is not same, then the routers are stuck in ExStart state. If you want to ignore the MTU, you can use the MTU ignore interface command. This is only for Cisco. I'm not sure about other vendors. All right. Then in the exchange state, they exchange the DBDs with each other, right? So master sends the DBD, the slave responds by sending its own DBD, right? And when the slave is responding, it will also set the M bit as 1. And we also know the significance of M bit now. Once the DBDs are exchanged, the two routers will go into the loading state, exchanging the whole database. When the whole database is exchanged, they will go into the adjacency state or full adjacency. So this is what the OSPF state is about. Okay. Now, what does it mean that they are in full state? Meaning that R1 now knows about these links of R2. R2 also knows about these links of R1. So when I do show IP route on R1, I will see R2's links. Similarly, on R2, I will see R1's link, meaning that the routing table of these two routers are now automatically populated using OSPF. And that is what we were discussing. The main work of any routing protocol is to populate the routing table of the router. The secondary is how to reach the destination as quickly as possible. So with this OSPF state or the exchange of database, the two routers now know about each other's links, thereby populating each other's routing table. All right. I hope there is no doubt over here. So with this, we'll conclude our session, and tomorrow we'll continue with the OSPF.